Alright, we're going to start section 9.2. This lesson is on simplifying square roots. This goes hand in hand with our previous lesson, 9.1, where we introduced the idea of square roots. Simplifying square roots takes a little bit. There's a skill to it. You have to know your perfect squares, and I gave you a long list of perfect squares in the last lesson. And we're going to use those perfect squares to simplify radicals in a way not all that different from when we used to simplify fractions, because we want them in simplest form being the easiest way to be able to identify the number. Alright, now I want you to consider the following problem that I have up here. I have the square root of 4 times the square root of 16. These are the principal or positive square roots. We know that the square root of 4 is 2. We know that the square root of 16 is 4. And of course we're multiplying and we get 8. Now I want you to look at this, and then I want you to look at this. And you can see all I've done is I've combined underneath the square root sign here. 4 times 6, we're going to do that first, that's 64, and the square root of 64 is 8. I get the same number both times. That's not a coincidence. That is by design. So what I'm going to do now is I'm going to introduce a very important property of square roots, the product property of square roots, which says that the square root of a times b is equal to the square root of a times the square root of b. And of course we can reverse this. We can go from here to here just as easily, with these stipulations that a and b are both greater than or equal to 0. We don't have any negative numbers under the radical signs. That's an Algebra 2 topic. So here's an example where I might apply this. You see here I have a times b. I'm going to think of this as 9 times 5. This is just an example. 9 times 5 of course is 45. I have the square root of 9 times 5. That's the square root of 9 times the square root of 5, which is equal to, now the square root of 9 is 3, because 9 is a perfect square. We can take the square root of it conveniently. The square root of 5 does not come out nice and neat and even. It's a little bit more than 2. So we have 3 times the square root of 5. Now you say, where's your times sign? Remember, when the number is right in front of the radical sign, that implies multiplication. Okay? So now, these two statements that I'm going to give you here are extremely important when simplifying radicals and simplifying square roots. A radical expression is in simplest form when, first, no factor, that means something that will divide evenly into it, of the expression under the radical sign. Now the expression under the radical sign has a fancy name. It's called a radicand. Radicand. Okay, and I'll use that from time to time, but that's the part that's underneath the radical sign, has any perfect square factor other than 1. Now notice here, this has a perfect square factor. 9 is a perfect square, right? 5 does not have a perfect square factor other than 1, and 1's not going to help us here. So that's why this part doesn't simplify. This part did, but this part does not. So no factor of the expression under the radical sign has any perfect square factor other than 1. If that's the case, that means we're probably in simplest form. And there's a second stipulation there. There are no fractions under the radical sign. You can't leave the square root of a fraction and have it in simplest form. And on top of that, you can have no radical sign in the denominator of any fraction. So you can't have something like this and call that simplest form, and you can't have something like this. There's no way we can have that and it's still considered simplest form. So we'll do some examples of simplifying radicals next. Alright, as we work these problems out, I want you to make sure that you understand that all variables that are in radical expressions, and you can see I've got a couple of examples coming up here with variables, they're always going to represent non-negative numbers. That means you're not ever going to have to worry about one of the variables maybe representing a negative number like -2 or something that could mess up the whole problem. So they're always non-negative. It might be 0 or anything greater than 0. Non-negative. Alright, now what we're going to do is we're going to use that first statement that I gave you about perfect square factors to simplify these expressions. I look at the number 45 and I think, what numbers divide into 45? Are any of them perfect squares? Now 1 doesn't count, so you'd have to consider 4, 9, 16, 25, 36, 49, and so on. I'll put more down if I need them. I look at 45, I look at those numbers, and I recognize 9 is indeed a factor of 45. I can think of this as the square root of 9 times 5. Now I'm going to use my product property for radicals. I'm going to write this as the square root of 9 times the square root of 5. And yes, this is the example from what I had before. The square root of 9 is 3, and this is the square root of 5. 3 times the square root of 5 is my answer. That's considered simplest radical form. Now in the next example, it's a much bigger number, so I have to consider a whole bunch of possible factors, because 360 might have factors up to 180, for example. So I look at these and I recognize right away the 36. 36 is a factor of 360. It's 36 times 10. Now I don't think there are any factors greater than that. I'd have to think of 49, no. 64, no. 81, 100, 121, 144, and so right up the line, 169, 196. I'm past halfway. 36 is the largest. You want the largest one to do this. I want to think of this as 36 times 10. This is the square root of 36 times 10. This is the square root of 36 times the square root of 10. Using my property again, this of course is 6. So I have 6 times the square root of 10. Now I know I mentioned before how it was a little bit like simplifying fractions. Obviously we're not doing the same steps, but the idea is to get a simpler, easier to understand version of the number. Alright, 150, the square root of 150. I started looking at these numbers, 4, no, 9, no, 16, no, 25, yes. 25 times 6 is 150. 36, no, 49, no, 64, 81. None of those are going to work. I'm going to use the 25. This is the square root of 25 times 6. This is the square root of 25 times the square root of 6. And this is 5 times the square root of 6. And I have simplified it. This is simplest form, this is simplest form, and this, for this last example here, is simplest form. Now I have one more like that, 63, so I'm looking for factors. Now by the way, if you can find no factors, the perfect square factors of the number, then it's already in simplest radical form. But I found one, 9. 9 times 7. So this is the square root of 9 times 7, which is the square root of 9 times the square root of 7. And of course the square root of 9 is 3 times the square root of 7. There's my guy. Now it gets weird, because now I'm throwing in variables right along with the number under the radical sign. But I'm going to work with the number first, just like I did these last 4 examples. I'm going to look to see if 48 has any perfect square factors, and it does. 16 divides into 48. Now I know 4 does also, but I want the largest one, so I want 16. I'm going to write this as the square root of 16 times 3, a to the second power. Now this is the square root of 16 times the square root of, now I'm going to go ahead and write this all underneath here. You can break this one apart, but that's my 4. That's what the square root of 16 is going to give me. Now the a squared is a perfect square. So when you take the square root of a squared, since a is a variable and represents a non-negative number, I'm going to think of this as 4 times a times the square root of 3. Or 4a times the square root of 3. Now I could have broken that apart differently. I could have written this line right here as, let's see if we have space, I'll put it right here, as the square root of 16 times the square root of 3 times the square root of a squared. And then you could have seen where the a came from perhaps a little more readily. I just left it underneath, as you will find out later on in an Algebra 1 or an Algebra 2 course. Sometimes it's easier to leave the variables underneath because you might have more than one variable to higher powers, and it's probably going to be easier for you later on to simplify it that way. Now in this case, I'm looking at 54. I'm trying to think of what numbers that are perfect squares divide into 54, and it's 9 again. This is the square root of 9 times 6t. Now this time the t is to the first power, so it's not a perfect square. I'm going to break this apart as the square root of 9 times the square root of 6t, and we know now that the square root of 9, several times here, is equal to 3 times the square root of 6t. There's nothing you can do with the variable in that case because it's to the first power, it's not a perfect square. Now with that comes the fractions. Now I mentioned in the second rule, you can't have a fraction underneath the square root sign. You can't have a square root in the denominator. But what I'm going to show you here is another property that we can use to help us to simplify. Now this expression right here, Would you agree 100 divided by 4 is 25? This is the square root of 25, and this is 5. But I also want you to consider, what if I broke this apart as the square root of the numerator over the square root of the denominator? The square root of 100 is 10. The square root of 4 is 2, and 10 divided by 2 is 5, and I get the same number. Not a coincidence again. So this leads us to another very important property involving square roots. Okay, that property is called the quotient property of square roots. Now, the quotient property of square roots says that the square root of a over b is equal to the square root of a all over the square root of b. So the square root of a fraction is kind of the fraction of the square roots. Now notice here, a has to be greater than or equal to 0 because we don't want a negative number under there. B has to be greater than 0, can't be equal to 0 because you can have 0 in the denominator. So let's use that property to simplify the next few examples. This problem right here uses this property. I have a fraction under the radical, you can't have that. So this is the square root of 11 over the square root of 4. And I no longer have a fraction under the square root, but I do have a square root in the denominator, which you can't have. But fortunately for us, this comes out evenly because the square root of 4 is 2. Now 11 doesn't have any perfect square factors, so I'm going to leave this as the square root of 11 all over 2 as my answer. That's simplified. Very similarly, part B here, this is the square root of 15 over the square root of 16. And if we're really, really lucky, the denominator is a square root of a perfect square, which it is. I can write this as the square root of 15 all over 4, because the square root of 16 is 4. Now 15 doesn't have any perfect square factors, so it doesn't simplify. My next example takes it a step further. This is the square root of 84 over the square root of 169. Now the square root of 169 is 13. 13 times 13 is 169. But 84 is not considered, the square root of 84 is not considered simplified because 4 divides into it. I'm going to think of this as 4 times 21, which is the square root of 4 times the square root of 21 all over 13. And of course the square root of 4 is 2, so this is 2 times the square root of 21 all over 13. Notice I had to do 2 steps there. I had to break it apart, take the square root of the denominator, and simplify the numerator. This is a little bit like that, in that this is equal to the square root of 32 all over the square root of n squared. Now the square root of 32 is not in simplest form. It's in the numerator. That's okay to have a radical in the numerator. It's not okay for here. But I know that 4 divides into 32 as well as 16. So what I'm going to do is I'm going to rewrite this numerator as the square root of 16 times 2. The square root of n squared, since we know n is a positive number, is n. Remember, all the variables that are under the radicals are considered positive numbers here. Now this is the square root of 16 times the square root of 2 all over n, and of course the square root of 16 is 4, so this is 4 times the square root of 2 all over n. My last example here is the square root of 49 over 121x squared. This is the square root of 49, and this is the square root of 121x squared. Well, 121 is a perfect square, 49 is a perfect square, and x squared is a perfect square. It's x times x. So the numerator just becomes 7. The denominator, the square root of 121, is 11, and the square root of x squared is x, and that is considered simplest form. And that will get you through most of the problems in the assignment. Now, I did want to show you 4 more examples. I don't think you'll come across anything like this right away, but I did want to give you a sneak peek of something you're going to see later on. The square root of 10 times the square root of 2 is equal to the square root of 20. Because I'm using the product property for square roots here, and then I can break this apart. Notice I can break, because neither one of these simplified, I can break this apart to the square root of 4 times 5, 4 being a perfect square. This is the square root of 4 times the square root of 5, and the square root of 4, of course, is 2, so this is 2 times the square root of 5. See the extra steps I had to do to simplify that one. Now over here, this is the square root of 54, the square root of 54. Now 54 over 42 like this, neither one of these are perfect squares, but they do have factors that are perfect squares. But watch what I'm going to do here. I'm going to write this as the square root, I'm going to make this one big radical here, 54 over 42. I noticed that some numbers divide into top and bottom, and I'm thinking maybe the number might be 6. 6 goes into top and bottom. So I'm going to divide top and bottom here by 6. I get the square root of 9 over 7, which is the square root of 9 over the square root of 7. Now, there's a problem. The square root of 9 is easy. That's 3. The square root of 7 does not simplify. So I'm going to show you what you do when you get a radical in the denominator that doesn't simplify. You multiply the numerator and the denominator by that same square root. I'm going to multiply the top and bottom by the square root of 7. 3 times the square root of 7 is 3 times the square root of 7. Oops, there we go. And the square root of 7 times the square root of 7 is the square root of 49, which is 7. And I finally got to a point where I don't have a fraction under the radical, and I don't have a radical in the denominator. Now, the addition-subtraction problem that I have here, we combined like terms back in our days of working with polynomials. Well, we're going to combine like radicals. See, these have the same square root. 4 square roots of 11 minus 3 square roots of 11 is 1 square root of 11. Now this part, 6 square roots of 3, these are different radicals. They're not like radicals, so you can't take it any further. But this expression does simplify by combining these, and it simplifies to that value. Now over here, these are not like radicals. So you figure, well, you can't do anything with that. Well, yes, I can. 12, remember, is 4 times 3. So this is equal to the square root of 4 times 3 plus 8 square roots of 3. The square root of 4, of course, we know that the square root of 4, I don't have much space, so I'm going to kind of finish it up here. Sorry, I'm squeezing it all in. Up here, the square root of 4 times the square root of 3 plus 8 square roots of 3. And of course, 4, the square root of 4 is 2. So this is 2 square roots of 3 plus 8 square roots of 3. Now they're like radicals. I've got 2 of them, I got 8 of them, I have 10 of them. 10 square roots of 3. So there's all sorts of different kinds of computation that you can do involving square roots. And you'll get better at it, but it will take a lot of practice, practice, practice.